Hello everyone, hello everybody. The introduction, you know my name, so Maxime MOREAUD. Today I will speak about artificial intelligence. I will try to explain how I understand artificial intelligence, and you will see for me it's not so complicated. So I hope at the end of this course you will understand a lot of things. And I will bring you some illustration for imaging, a lot of imaging, microscopy, and digital holography, and so on. So we'll speak about that. It will be two parts. The first part, I will give you an introduction concerning AI. I will explain you what is a convolutional neural network, why we use it to do a lot of things. It's the first part, so don't hesitate to ask questions when you want, okay? We will do a short quiz after this session with Kahoot. I hope you know what it is, so I will explain how to use it. And in the second part, it will speak about illustration. So I will give you a lot of examples of how to use artificial intelligence in case of imaging techniques, and with a lot of illustration in material science, because I work in this field. So I will bring you a lot of examples with a lot of cases in materials, but also a little example with biology samples. Okay, so I will start. So I hope it's okay with the video conference also. Perfect. So for me, if you need, it's one of the big ideas you need to understand today. For me, artificial intelligence, for me, it's deep learning. I will speak a lot about deep learning, okay? And in deep learning, you can see deep learning as a way to transform one data into another data, okay? But you don't need to explain how you will transform it. So it's very different. It's a big difference compared to other mathematical fields, because in other fields you try to define a model, mathematical model. You try to understand everything to explain what you want to model. With deep learning, it's not the case. You just want to transform a data into another. So you don't explain how, but you need to have examples. So you show some examples. So then I speak about transform one data into another. To be very specific, I speak about transform one image into one other image, or it can be a signal into another signal, or it can be an image into a vector, or a signal into a vector, or vice versa. Okay? So it's not very illustrative. So I will give you some illustration or how we can transform a data into another. So for instance, you can see at the left an imaging of an atom molecule. It's gold nanoparticles. Okay. So what you see with dots in black and white, it's some gold atoms, okay? So you can see a spatial arrangement that is particular. So you can transform this image into a vector, and this vector can give you information about the configuration of your nanoparticle. So in the way of thinking, you transform an image into a vector. And with this transformation, you can explain what you see. Another classical example can be you give an image to Google, and Google tell you what you can see in the image. For instance, you put an image with a tree, and Google say you in this image there is tree, or there is cloud, or there is a car, something like that. In case of material science, we can use it to, for instance, estimate or give the spatial arrangement of some atoms. Another example, to transform an image to another image, It's to, for instance, at the left, you see something that is an observation of catalyst support that can be used, for instance, for the transformation of plastics, the refining of plastics, for instance. And you can see on the right, you see another images, but this images is more simple. You just see black and white pixels, and you look at, with the white pixels, some specific porosity arrangement in the left image. So you transform an image into another image, and you can use deep learning to do it. I will go back to this example later. Another images in example in the fields of biology. Here you can see on the left side some neuron observation with dendrite. Okay, it's observation with digital holography. So what is particular in this image is that you see some neurons in yellow, and you see some connection here with the dendrite, but you see also a lot of noise. Okay, you have some random noise, but you hear me? No. Okay. Sorry for the technical problem with the microphone. Okay, so you see some neuron and dendrite, okay, in these images, but you see also a lot of noise. Maybe it's not very visible in the audience, but with the video conference, I see it's more clear. You see some structural interference due to the samples you observe, okay? And it can be difficult to be able to observe all the connection between neurons. And what is interesting is that you can transform this image into another image using deep learning techniques to make some specific denoising of this kind of image and obtain some things on the right side with less noise, maybe no noise in some case, and you can see more exactly all the connection between the neurons. So it's a very difficult task here with classical image processing techniques, and we can solve it very well with deep learning. Another example, we will go back also later. On the left, you see some microfluidic experiments. So here it's a micro gauntlet that go into some microstructures at the micrometric resolution. Here you can imagine that this black dot moves into the microstructures, okay? And you can use deep learning, so to transform this image into not an image, but a duo of image that can give you the displacement vector of each of your particles, of each of your nanogauntlets, okay? So here I represent on the right the modulus of the speed displacement vector of the object, but you can estimate a lot of things with this. So you transform an image into displacement field, so it can be seen as a duo of image. So it's some example of transformation. So in my class, we will see how to do all this kind of example and how it works. So I will start with a brief history concerning deep learning. Then we will start for real with CNN, so it deals with convolutional neural networks, okay? I will make a focus about the convolution operation, because we will see that it's very important to use this operation in particular, and why it's important in this case. We will see also multi-scale aspect of the convolutional neural network that is very important and that is very similar with the human vision. And we will see how we can learn from data to optimize these operators. So I think we will stop here to take a pause, okay? And we will come back after the pause with some illustration of the usage of these techniques. So I will speak about a lot of illustration from IFP-EN, and I will make some conclusion. So repeat, don't hesitate to ask questions when you want during the conference. So a brief recent history of artificial intelligence. So you can remark that it's a young domain. It's less than 100 years, so it's very young. It starts. We can say it starts from 1943, 43 years, with the first concept of neural networks. In this period, it's the concept. It's used only neuron as an operation that you have some inputs. Okay, so you take this input, you multiply this input by some coefficient, you make an addition. So it just can be seen as a weighted addition, and then you apply at the addition a threshold operation. So it's called a neuron, okay? And you can use this neuron a lot of times. So you can use a neuron that is an input of another neuron, and so on. So it's the first operator that will be created at the earlier studies. So in 1957, we formalized this composition of operation as the perceptron. That it's maybe you already learned about this. So there is some starting of in research in this domain, and in 1970 we have the first, what we call the first artificial intelligence winter. So it's, as you can see in my slide, you have. It's not very visible, but you have some curve of interest of the domain. So a start of interest of the domain, and here between 70 and 80, you have the first disinterest of the community for this kind of domain. And if you need to remember one thing, it's here that the community disinterest of this kind of techniques, because if you use only perceptron with this kind of operation, you are not able to modelize some simple operation like XOR operation. You are not able to modelize this kind of operation. So a lot of people say it's not very useful to have this kind of research, because we are not able to modelize simple operations. So there is no way, it's a bottleneck. But in the 82, some people, not from mathematics, not from informatics, but from physics and applied mathematics, go back to these techniques and apply this for a physical case. And there is a small interdisciplinary teams that continue to use this technique. So it's come back to be interesting. So this community grow and grow. Some remarkable that in 87 we have the first conference that is called NIPS. It's a small conference at the beginning. Now it's a very, very big conference for AI, one of the biggest. In 90 we have also the interest growing, and we can see first small model of image and words, but we have a lot of lacks of computing and power, with not the good way to construct maybe the learning database. So the results are not very spectacular. And in 2020, we have the second AI winters. And what you need to remember is that we have this disinterest concerning artificial intelligence, not because it's not the AI operation are not able to do some things, but because other methods from computer vision are propose better performance. For instance, you have in this period, you have all the Fourier domain research with wavelets. You have all the mathematical morphology domains in computer visions, coupled with statistics method or machine learning methods, if you want, with standard vector machine and so on, that propose better performance. That's only deep learning techniques. But in 2010 and in 2012, we have an explosion of results with CNN because some people continue to use it and they increase the usage of this operation, of the operator, and especially with convolutional neural network in this case, because it's well adapted for image processing. We will see why it's very adapted for image processing or signal processing. And in 2012, this kind of method go very high ranking concerning all the other methods. So from this date, all AI techniques, so deep learning techniques, are better than other traditional methods from computer vision, and it's continued to grow. Just now we use in. I'm from the computer vision domain, and I use day-to-day the deep learning methods to solve some very difficult problem. So last date I want to mention is 2018 with the Turing Prize given from Yann Lequin, Yoshua Bengio, and George Hinton for their contribution in the field of deep learning. Okay, and last year George Hinton received the Nobel Prize in chemistry for his work for deep learning applied to chemistry. So all this history, it's quite important because it gives you information that it's a quite new area. It's grown very fast the 10 past years, and it is very important because it can solve some very difficult problems that before we are not able to solve it clearly. So we continue with the real introduction, so the real start of my talking. So I will speak about convolutional neural network. I will give you an overall description, and I will speak a lot about convolutional operation. So don't try to understand in detail this first slide. We will go back later in this kind of architecture. So I will present you what is a convolutional neural network. So you will see a convolutional neural network. It's like a set of operation with convolution, and it can divide in two parts. We have a part concerning the image description. So we'll see this operator will try to describe what is contained in your image. And you have a second part with simplification and classification task. So you have all these first parts concerning the learning of description from the data. The idea is to take some description of the data and simplify the representation of the data. And then you have a second part that can make, from this description, a classification, a division into several classes. Okay. So to be very specific, in the input, I will take a very specific example. You can see an input, we will use an image, and an output, we will have a probability to belong to a class. So you can see as a vector at the output. Okay. So we transform an image into a vector with this kind of operation. So in CNN, what is very important is that we use convolution operation. And why we use convolution? It's because an image or signal, because it can be seen the same way, or volume. In an image, the location of point is very important. So the information carried by two close points, okay, is very different from information carried by two distant points. For instance, if you see the image at the bottom of my slide, you will see an image of 6 by 6. Okay, here and here. You have the same number of black points. Okay, but if I ask you to explain what you see on the left and what you see on the right, you can tell me directly. Here you see a 6, and here you see a letter H. Okay, but to make this answer, you don't count the point, but you have to inspect carefully the localization of the point between waveforms. Okay, so you consider a point with its neighborhood and its context. And also, the near neighborhood should be watched carefully, and the far neighborhoods with less attention. It's similar with human vision. Then I ask you to watch these two images. Okay, you are able to see the 6, the H. But if I ask you now to tell me what is the color of my jacket in this seat, I think you are not able to answer. Now you see my jacket, so you can see it's blue, it's dark blue, okay? But at the beginning, if you ask you to focus on 6 and H, you'll see on your fields my jacket, yeah, but you are not able to set the color or something like that, because you only focus on some parts of the localization of the image, okay? And CNN work like this. So we will see O with the multi-scale aspect, but with CNN, you focus on some parts of your image with a lot of detail, and you see some distant and some context with less attention. And it's similar to human vision. So if we go back to convolution, I can give you the definition of a convolution. So it's like this. You have some function on the right. I give you the discrete formulation. Okay, you have a function on the left. Sorry, and you have what we call a second function, small function here with that is called convolutional kernel. And the operation we do with convolution, it's only some multiplication and addition. Okay, you have the detail of the operation that is given here. I hope you all know what is convolution. So if you don't know, it's not a problem. You make the discovery of this operation now. It's multiplication and addition. So it's a way to define a multiplication between two functions. So here you have a value, and to make a convolution, you can see on the right side, you take the second function and you displace this function upon the first function, okay? And in this way, you can compute a series of values. For instance, here you have an image, okay? You have a kernel, and you can compute for each position of your kernel the value of the operation, and you can construct that we called in computer vision and in CNN domain what we call the feature map. So feature map is just the value of the convolution. We apply a kernel into an images. Okay. So then I explain that. I explain something very mathematical, very abstract. It's a real definition of convolution, but I'm sure you don't understand why we use convolution in CNN. Because with this explanation, myself, I don't understand why we use convolution if I explain it like in this way. So what is important is this slide. And one major idea you need to remember after this lecture is that convolution can be seen as a similarity score. So convolution operation is like you try to compare two things. So here it's two functions, and you want to see if these two functions are similar or not. Okay, you can see the convolution like this. And if it's similar, you will obtain a high value with the convolution. If the similarity is not very very high, you will obtain a low convolution score. For instance, you can make a convolution with the same images. You will obtain a very high score, for instance, 1. If you make a convolution with some image with some similarity, you will obtain some things low, below 1. And if you try to do the convolution with some images that are more and more different, you will decrease the score of the convolution. Okay? You can see a more specific example on the right. Here we have an images of a house with a lot of structural, geometric structural orientation. We have some orientation, vertical orientation, horizontal orientation. And as you can see, if we change the kernel, so if we change the function, we can compute some results that give you indication of some orientation. You use specific kernel here to compute similarity with horizontal orientation, with vertical orientation, with diagonal orientation. Okay, and you can see the result with the animation here. I hope it's clear for you. With this, using some specific kernel, you will obtain some specific information concerning the textural information of your images, okay? So we use convolution in a convolution neural network because we want to compute some similarity with specific kernel that is representative of textural information. And what is important also, it's that another idea that is important is that to describe an image it's a complex data. So you don't need only one description with one kernel, you need to use a lot of kernel. So in convolution neural network, we will use a lot of kernel to describe our data. So here, we can see what we obtain if we applied a convolutional neural network with a specific image. Here, I use also an image of a cat. Okay? And I just focus in the first layer. So I don't explain it, but in convolutional neural network, we have some what we call layer, and layer are a series operations. In the first layer, we have convolutional operation. Then we have a second layer with another convolutional operation, and so on. So we have an iteration, composition of some convolution. And in the first layer, you can see, you obtain, if you take these images, some results that we call feature map. And as I mentioned before, you can see some result from this image that is with specific information concerning some orientation or some specific texture of your image. For instance, here you can see with this feature map, more response concerning the horizontal orientation, and with this one, more specifics with vertical orientation, okay? So we use convolutional to compute similarity map, and we use several convolution to obtain a series of description. Okay, I go too fast. So what is important also in convolutional neural network is the multi-scale aspect. So if you remember, with my example with the 6 and the 8, I explain you with human vision, you see carefully some things in the image and less carefully some distant things, some context. So why we use multiple layer in image description? So we need to watch carefully the near neighborhoods, okay? And the far neighborhood, we need to observe it with less attention. It's very similar to human vision. So the first layer can be seen in CNN as a local description with details. Okay, so we compute directly some response from pattern from the image. And with the second layer, we don't work anymore with the image. We work with the description of the image. So we have the description of a group of patterns of the first layer, and we look at a larger area with less detail. So we don't look directly on the image, we look at description of the image, and we also reduce the size. I will explain how just at the end of this slide. And we make description of the description. Okay. So that we can call abstraction. So we don't try to calculate some description directly on the image, but with the description of the image. So in the third layer, it's like the second layer, but with the size that is also reduced. So to reduce the size, we usually use what we call max pooling. So to make a simplification from an input to an output, to reduce the size of size 2, we take, for instance, the 4 value in the input images, and we take the max on the 4 value to compute the output. Okay, it's that we call max pooling. So you can see it like between several responses, we take the most informative. So we take the maximum of the intensity. Okay, so first layer we compute directly characteristic on the image, and with the second layer and third layer, we don't compute it directly on the image. We compute it from already some description of the image, and also we reduce the size, so we reduce the detail contained in the image. So you can see with this animation, in the second layer, third layer, fourth layer, fifth layer, you can see some feature maps. And as you can see, the feature map are less and less, are with less and less details. And you can see some abstractions in the sense where you, in the deep layer, you are not able to recognize anymore a cat, okay? But in the deep layer, you have information concerning the context, global context, global texture of your images. So another way to explain it, in the first layer, you have some high frequency content, high frequency information, and in the deep layer, you have low frequency information. I hope it's clear for you. And a CNN, it's composed only with this kind of operation. You have some convolution, okay? You have some 2D pooling is that we just see, it's max pooling, okay? And at the end, we have what we call fully connected layer and some activation function. It's just to make a classification. So, as I explained in the beginning, deep learning, it's a way to solve some difficult problem. And we don't want to explain how solve this problem. We just want to show some example to solve this problem, and we want an operation to mimic the solution of this problem for another data. So the idea here is to use the operator I just presented, the convolutional neural network, and we don't want to, and we don't know how, we don't know the kernel we need to use, because we don't know at the beginning what is important to extract from the image to solve a specific problem. So we will need to optimize the kernel, for instance, and to optimize the classification layer at the end with a specific technique. So we will use the data available. So we have many parameters to set. We have the weight of the convolutional kernels. So it will define which patterns are relevant for a particular task. And we have also the weight of the classifier neural network. So it's the end of our CNN. Okay. So it will be complicated to explicitly define this parameter. So let's leave this works to a particular algorithm that will learn this parameter from example. Okay. And we have a lot of parameters to learn. So we require a lot of example data. A lot of example data, it's not that you need 1,000 of example, but you need some example. It can be 2, 3, or 10 example, and you need numerical tricks to create some numerical data. So in practical case, you don't need 1,000 of images usually. You need 10 images, for instance, but you need some specific trick to use these 10 images to create some virtual over images and construct a data set to be able to learn some things from the data. So to optimize the parameter of the neural network, we use that we call a stochastic gradient descent. It's an operation that is come from the control field domain in the 1960. It was not concept at the beginning to optimize some neural network or some convolutional neural network, but to optimize to solve the parameter you need to use in the composition of function. And CNN can be seen as a composition of function. So it's why we use this kind of trick to optimize the parameter. So to do it in practical way, you need to have an input images, okay? So you will use your CNN to compute an output. This output, you will compare this output with the ground truth output, okay? So you have a learning database, okay? So you know the input and the output. So you have the input, you compute the output with the CNN, you compare the output with the ground truth. It gives you an error, okay? And you use this error to correct the parameter of your CNN. And the correction is very basic. The idea is to answer this question. How can I modify the parameter of my operation to, if I take this input again, I obtain the same output as the output I want. Okay, stochastic gradient descent is just a way to modify your parameter of your function to modify the output to a specific value. And you use a chain rule. We use a chain rule to compute and backpropagate step by step for the convolution and max pooling layer. I don't go into detail concerning the formulation to compute the gradient descent for the convolution, but it can maybe it's on my slide, or I can give you some details in some additional slides if you want. Okay. So I speak a lot about convolutional networks, and I take example where I transform an image to a vector. And at the beginning of my lecture, I explain you that I can also transform an image to an image. So now I will give you it's not the trick, but the idea to obtain an image from an image. And the idea is like this. So I illustrate it with the very well-known UNet architecture. But what is important is that this kind of architecture to obtain image from image or signal from signal is that we call an encoder-decoder. It's completely normal that we call it encoder-decoder because you can see it as a two-step operation. You have the first step. It's exactly what I explained before. So you have some input, okay, and you have some convolution, then reduction, spatial reduction, convolution, spatial reduction, convolution, spatial reduction, okay. And at the end, you obtain a description in sort of vector, okay. Is that we call encoder. You encode your image into something that is quite similar to a vector. So you learn description of the data and you obtain a simplified representation of your data. Then you have a second part in your operation. It's the decoder part, okay? And it's quite similar. It's very similar. You have also convolution, but you replace the the space reduction by an upscale operation. Okay, so you have convolution, upscale, convolution, upscale, convolution, upscale, convolution. If you have the same number of downscale and upscale, you obtain the same dimension from the data, and you can reconstruct from an image an image. Okay, what is specific to UNet is that you can see here, it's a gray arrow. Yeah. So the idea is to take some information from the encoder and put it directly in the decoder. Here it's only you take the result and you put it in the output. Okay, I don't go into detail, but it's important. This kind of architecture is very well used because with this arrow that we call shortcut, it increases the performance concerning the optimization procedure, the gradient descent procedure. Ask me a question if you want. I will be too long. Okay. So here I bring you some information concerning convolution, multi-scale aspect, how to transform convolution, an image into a vector, an image to an image, and just to illustrate some things to open some idea. You can use also this kind of techniques to process volume. Okay, so here is just an example. Or you can do the same as before for volume. So the idea is very simple. You change the 2D convolution by 3D convolution, and you obtain something that can be used with volume. So you can transform a volume to a volume, okay, using something that is quite similar I just presented before. It's that's called VNet, okay. So you have something that's learn a description of your volumes, and you have a decoder that constructs a volume from this description. So the downscale is the same, upscale is the same as in 2D. It's trivial to obtain it, but that it can. What you need to remember is that it requires a lot of parameters to optimize because you increase the size of your kernels. It's not anymore 2D kernels, it's 3D kernels. And it makes a lot of parameters to optimize. So in my experience, it may be intelligent to transform the problem into 2D problems. Maybe we will see if you have time in the application. And you can solve a lot of 3D problems only with 2D architectures. Okay. Perfect with the timing. I propose you to stop the first part here. I can take some questions and we can do a quick quiz if you want just after. So maybe you have some question concerning the part I just present.
Yeah, so I was about to ask about the 3D architecture. So you said that for some problem you were using 2D architecture and it's fine, but I guess that for some other problem you still need to use 3D architecture. So what are the kind of preprocessing or steps you are using to make it less costly?
Yeah, okay. So so it's less costly with 2D architecture because you use very simple. You use 2D kernel, so it's less parameter to optimize. Okay. So you're right. In 3D problem, you need to take into account of the 3D information. It's important. For instance, you have a volume to process. So in some cases, it's not possible to only take a slice from your volume and process it. You lose some information, some very important information. It's not possible to take the decision. But the trick or the way to solve the problem is, as I explained before, for me, not for me, but deep learning can be seen as transform something in data into another data. I explained an image can be transformed into an image, but you can have also a series of images can be transformed into an image. So the idea is not to take only one slice, is to take, for instance, the slice you want to transform, but to take also the previous slice, the next slice, or maybe the 2 previous slices or the 2 next slices. It depends on the problem, okay? So you take in your input several slices, and you compute in the output 1 slice, the slice of interest. And in this way of take the problem, in my experience, you can solve lot of 3D problem, and the benefit is that you can train your architecture very easily, because it's a standard unit and it can be trained very efficiently with less number of samples in your database. It's one trick to do it. I hope it's okay. Yes. Maybe another question.
I understand that you have been describing convolutional neural networks. So in each layer, the operation is a convolution. Then between the layers, there is something else. You told about max pooling. So there could be many things. But inside a given layer, it's always a convolution. However, in the desired outputs, it cannot be only convolutions. So my question is, where do you incorporate non-shift invariant operations?
Thank you for the question, because for my lecture, I make some simplification, because I just want you to understand the main idea of this operator. And you're exactly right. It's not only convolution. It's also, but it's not very difficult. You have convolution, but also normalization in some case. And you have also some threshold operation, okay? So I hide it, but if you read carefully the slides, you have the information. So here in this block, it's not only convolution, it's convolution plus that we call ReLU. So it's just a threshold. So for instance, ReLU, you have the result of your convolution and you take only the positive part. If it's negative, you take 0, okay? You can also, that we call batch normalization. It's only a normalization to don't have some values that go to a maximum and stay at maximum. So, but the idea is the same. The idea is to compute similarity, and to do it, we use convolution, but we use also threshold and batch normalization to be able to extract some things that can be more complicated. You can see a lot of this, a lot of explanation like this. With this threshold operation, we incorporate some non-linearity into the operation, and it's very important to use it, because if you take only convolution, okay, and you don't take ReLU operation, you don't take match pooling or something like that, you just make a regression, linear regression, okay, and it can be useful to make a linear regression. It can solve some problem, but it cannot solve very difficult problem. So the idea is to incorporate some non-linearity, and it can be seen as you make a regression but with a very complex operation. Okay, maybe I hope I don't go too much in the detail, but yeah, you're right. It's not only convolution. We have also some activation function to bring some extra functionality in your operation.
Yeah, I have a question about designing the neural network. So would you have any tip that when you choose like activation function or loss function to have the better performance, something like?
Yeah, exactly. So concerning the design of these blocks, nowadays there is lot of question. It's what I mentioned, 8 plus batch normalization. So it's convolution, batch normalization, and ReLU. And it's work approximately for all problems. But what is important is to design correctly your architecture concerning the number of features. Okay? It's like you see here. I mentioned some illustration concerning the number of features you need to calculate. So if your data is very complex, you can see it like this. Your data is very complex concerning the textual information or the composition, okay, of your problem. You have a lot of variety of possibility of arrangement in your data. It's important to have a lot of feature map. Okay, so you will use a network with some high number of feature map. Second thing that is important is the number of layers. Okay, is that we call the way of your architecture is deep. Do you use 2 layers, 3 layers, 4 layers, 5 layers? And here it depends of the size of your object of interest of your in your image or in your data. If you understand well here, if we go from the description, okay, we have a convolution. In classical architecture, no, it's only 3 by 3 convolution. We use almost in every architecture, no, we use only 3 by 3 convolution. Okay, so you take from a vector, you have a 3 by 3 convolution. So it's like you increase by size 1 your vector. Okay, you have a max pooling operation, so you increase by the size 2. You have a convolution, you add 1. So if you go from the vector and you go in reverse in your architecture, you go from, it's like you go from 1 pixels and you increase the size of your pixel. So the number of layers correspond to the size of what you are able to see for each pixel. For instance, if you have only 1 convolution, for 1 pixel, you are able to compute only information from the neighborhood. And that's all. It's not possible to have information from 1 pixel to another pixel that is very distant. But if you use, for instance, 4 layers, you are able to compute some characteristic from the pixels and its direct neighborhood, and also the characteristic from your pixel and some less distant pixel, for instance, 20 pixels or 30 pixels. It depends on the number of layers you use. Okay, so you are able to compute this kind of characteristic, but you don't compute this characteristic with lot of details. It's not important. So you use an abstraction to compute it. But the number of layers depends of the size of your object of interest. Okay.
Okay.
So we have some rules to define the architecture you need to use in your to solve your problem. Exactly.
Thanks
Thank you
so
for the
much.
question. C'est comme ça, c'est pas gênant. Ouais. Thank you. So we'll continue. Maybe before starting the next part, with the coffee, some question comes up. It's time if you have some question concerning the previous part. No, it's okay. So we will continue. So now, in this part, I will provide you some illustration, some practical illustration of using deep learning to solve some problems, some complex problem. So in the case of application from IFPN. So in the first part, I will provide you some example concerning what I call object classification. So it's classification. So the idea is to transform an image, or it can be a signal, into a vector. So the idea in this vector, you are able to describe the contents of your data. For instance, here you have an image of a tree, so you want at the end that your vectors containing the information give you information that there is a tree and no car, no bird, no cat, and no banana, for instance. Okay. It can be also a way to predict some property. So here, in this case, for classification, you want the CNN to provide you some binary, so probability, okay? But you can also use the CNN to provide you some value, scalar value, and the scalar value can be linked to a property. I will give you some example. So first example is that you can use CNN to make robust classification of nanoparticles. Here present you some result from Romain Moreau. He's a PhD student with myself and some colleague from ONERA and LEM at the LEM laboratory from ONERA. So we use some images that obtained from TEM, so transmission electron microscopy with high resolution, okay? And he used CNN to estimate from this observation what is the configuration of the atom of your nanoparticles. Here I represent you the 3D representation, but concretely, the CNN provide you a vector of probability for a given configuration, okay? So it's a very interesting way to use CNN to make some classifications that are very difficult in a classical computer vision domain. Another example that is done at IFPN, it's another work by another PhD student. It's from Florent Hafner. He's on my supervision. He works at IFPN. So he used CNN to estimate a property from a signal. Here he used a signal obtained from near-infrared spectroscopy. Okay, it's this kind of data. It's not an image anymore. It's only signals. Okay, and he estimates from this data a property that we call Cetan number. This Cetan number is a property that is very useful to characterize the quality of some treatment to the process from crude oil to gas oil or something like that that can be used in your vehicle. Okay, so it's some things that it classically done using a chemometrics approach, so it's statistic approach. And in his work, you can see the reference at the bottom. In this work, we have shown that with CNN, we were able to be more robust. We have better classification, and we can use classification with several types of array, and we don't need to make a lot pre-processing that is usually necessary with a chemometric approach. Okay, so we go back to images. It's not very beautiful in the projection, but here we see some microfossil. So it's some rocks with some fossils inside. And we use here CNN to detect and classify the microfossil. So here I explain you, I will use this example to explain how YOLO, for instance, if someone knows in the audience, YOLO is a detection CNN to make some detection like this. I explain here, I'm in the case of, I want to transform an image into a vector. And here I show you some box to define the object in the image. So how can I use a vector representation? So I not transform an image to an image. Here I transform an image into a vector. So to make the object detector, I use this specific trick. I train the CNN to extract from the image 4 coordinates, 4 numbers. The 2 first numbers are the coordinate of the point of one box, and the 2 second parameters are the weight and the height of the box. In this way, I can learn CNN to extract from box of interest of my object from an image. Okay, it's not segmentation. It's a real classification networks, and we use it to make some object detection. And I use also another parameter of the vector to classify the type of fossil I detect inside the rocks. Okay, so it makes some from my colleague from TELUS. It's a consortium with IFPN and some other academics and industrial where we provide some tools specifically with AI to solve some problem in geoscience in particular. Okay, so another example is that we can use CNN to make classification of rocks. Okay, so here you put an image and you ask the networks to provide you the kind of rocks you observe. Okay, you can go to this website to see more. Okay, maybe it's not. It just the network is not already available. It will be soon available. You can visit the network, the website, to see some information concerning the availability. Okay. So I'll go to another very useful application of the CNN is semantic segmentation. Use segmentation if you prefer, if you don't want to go too much into detail. The idea here is to transform an image to another image, but the image you obtain is simpler than the first one. For instance, you have a standard image with a lot of intensity, variation of intensity that represent here a tree and some sky and so on. And you want the networks to divide the image in 3 parts, a part with the tree, a part with the sky, and a part with the ground, okay? So that we call segmentation. X pixel here, we just contain an intensity that corresponds to a class of object. So we use it to make some segmentation of very complex observation. On the left, it's not very easy to see, but it's some materials. It's a support. It's a catalyst support. It is used for the plastic refining or for the petroleum industry in general. It's a well-known materials support. It's an alumina support, exactly. And in this support, there is some variation of the porosity, density of porosity. So in some place of your materials, you have some big hole, yes, where you have some big porosity, and in other localization, you have some dense material, so you have a very small porosity. So the porosity go from the micrometer scale to the nanometer scales. Okay, so the idea is to localize the low density porosity. Okay, so where there is some big hole. Okay. And we use some CNN to do it. It's some work from my colleague from IFPN and former PhD student Adam Amoumi, and also Alexandra Glowska with the collaboration of UCL from London, where we provide the result inside also the plugin platform. I will explain it. I will come back to plugin later in the slide. So here, what is interesting also is that we use something specific to make the segmentation. We make the animation in this way. As you can see, we use some patch. Okay, we don't estimate directly the result from the image. We divide the image in small images that we call patch and make the prediction. This way to make the process is it increase the accuracy of the segmentation, but it's also very interesting to make the learning steps. With these tricks, using image and extract some patch from the image is used to transform only 10 images in the database into a database of more than several thousand of patches to train the CNN. So it's a usual trick to increase the size of your database. Then you have only a few images to make the learning steps. Okay. So some works from a colleague from Laboratoire Berkerien, just near from Telecom, especially with Christophe Ducotet. It's the work from Cyril Lee. That's it will, yes, it will work from 3D. We have some question previously concerning 3D. Here we tackle the problem of the segmentation of 3D volumes obtained with electron tomography. If you know tomography, it's not X tomography, standard tomography. It's a tomography obtained with transmission electron microscopy. Okay, so it's here. What you see here, it's only a grain of materials that is very, very small. It's only 500 nanometers. Okay, these techniques provide some volumes, 3D volumes at the nanometer scales. And the issue with this acquisition method is that it provides very nice data at the nanometer scale, but it provides also a lot of noise. So it's very difficult to segment. And so we use CNN to make the segmentation. And here we use also a specific approach that's called contrastive approach to make the learning steps available only with very few annotated data. In the idea here with the work from Cyril, we just need to provide one slice of your volume, and you don't need to annotate all your slice. You just need to annotate a portion of your slice. You give it to your networks to learn the weight of the kernel, as we see this morning, and you obtain something that are able to segment all your volume. It's an example where we don't take into account the 3D information. It's not necessary in this case for tomography electron segmentation. We just need to work with slice. It's sufficient to tackle this problem. Okay, I go back with my previous example, and I show you that we can go with more precision that only make detection of object. We can also segment the object. So with this kind of information, here we extract automatically some kind of fossils inside the works. And then you are able to make semantic segmentation. It's very interesting because you can make some morphological analysis. So you can compute the size of your object. You can compute some characteristic concerning the anisotropy or isotropy of your object or something like that. So you can go to much detail into the characterization. Okay. Another interesting example for me, because I think the problem is very hard to solve with classical image processing, and with deep learning, it's solved very accurately. It's a work done by my colleague Cyril Cassard at AFPN. As you can see in the right, it's some bubble observation in a reactor. Okay, but there is a lot of bubble. Okay, the bubble are in black. Okay, you have some reactor, and you have some light that and a camera at two opposite sides of your reactor. Okay, and you observe the bubble in black, and you want to extract the bubble. Okay, and you want to extract only the bubbles that are in focus in the images, and you can do it by deep learning. That is very interesting. That you just need here for this work. Remember, Cyril used only 2 images to make the training steps. And with only 2 images, you obtain this kind of result where you can extract all the bubbles that in focus. Okay, and it's very interesting because with this kind of information, you are able to characterize your bubble, so the size of your bubble, the morphological characteristic of your bubbles also. And it's very important to characterize some things that can mix some air in liquid, and it's directly linked to the characteristic of your bubble. So it's a very new, interesting tool to characterize some reactor and some mixing for liquid or air liquid processing. Okay. Another illustration in the field of microscopy It's only, as we see previously, it's some image obtained with transmission electron microscopy. Okay. Here you can see some catalyst support. It's also an alumina support. But in this support, you see also some black sheet here. And these sheets are that we call active phase in your catalyzer. Yeah, it's where the chemical reaction will be take if you use this kind of materials. And we use CNN to extract only the MOS2 sheets. Okay, so we only want to extract the active phase. So this is the kind of result you can obtain with CNN. So it's very interesting because with these images, you are able now to count the number of sheets. You are able to measure the length of your sheets, and these characteristics are directly linked to the performance of your catalyst at the end. So it's a work done by my colleague Denis Guillaume and Loïc Sorbieux, and also other colleague Virgile Rouchon, especially. So it's done at IFPN also. Okay, another fields of application. We exit the fields of material science and we go to the microplastics. So it's a work done by Sébastien Rouet. It's my colleague. It's project leader in the microplastic fields at IFPN, and he works on techniques to characterize the impact of microplastics in the environment. So it's one part of his project is to be able to characterize the number of microplastics you can encounter in the environment, for instance, in the beach. Here you can see the usage of CNN, exactly what I present, UNet-style networks to do the job. You can see very complex images, and here, I hope it's okay with the video, you can see in yellow the extraction of the microplastics that are present in the image. Okay, so it's another example of application of segmentation using CNN in a very complex background image and so on. Another image done by a PhD student, it's Adrien Moncomble. It worked with IFP and InPQ and Onera LEM also. And he used CNN to be able to estimate the number of given atoms in a column of atoms. Here you can see on the left some very high resolution image obtained from transmission electron microscopy. So with the dot, the white dot corresponds to atomic columns. So you have a series of atoms, okay, that you observe. And what you want to estimate is the number of gold atoms in these columns. Okay, and you use a CNN to do it. So it's not exactly segmentation. It's almost segmentation. So here you use a network to estimate a number at each pixels, and this number needs to be correlated to the number of atomic atoms, gold atoms you have in these pixels. Don't hesitate to ask some question, because maybe I go too fast, some example, and if you need some explanation, don't hesitate. Okay, so I switch to another type of application. A very important application and where CNN solves a lot of big problems in the noise reduction, or what we call resolution enhancement. The idea here is to transform an image into another image. But for instance, you have an image with poor quality at the input, and you obtain at the end an image with high resolution, or without noise, or at least you reduce the noise in your image. Okay, So here we go to the biological application where we apply noise reduction. It's a work done in collaboration with Cerveau. Cerveau is a laboratory from University Laval at Canada. We work together to put in place this kind of approach. It's something that I present at the early beginning of my talk. The idea is to be able to denoise some observation obtained by digital holography. So here we have observation of neuron and dendrite at the left. It's here. And we use a CNN. It's a specific CNN. It's like a UNet, but a little more complicated to be able to extract very accurate details. And we obtain that we call us virtual PDHM images. That is an image almost without noise, and we are able to extract the connection that we are not able to extract it correctly in the first image. We call it virtual PDHM because here we make very hard work to construct the database. We use a physical denoising method to construct a database. So we use polychromatic digital holography to denoise physically the image. Okay, so the idea is to take 20 images of your samples, varying the wavelength of your laser to produce the hologram. Okay. Doing like this, you are able to produce some structure and noise that are not the same because it's linked with the wavelengths of your laser, and you are able to produce some images that are different. And if you take the average of all your image, you obtain some things without noise. Okay, you denoise experimentally, physically your image, but the drawback of this method, it's a very time-consuming. And it's not very easy. It's not possible to do it with conventional microscope and with conventional laser. So the idea here is to provide something that numerically do almost the same jobs. So we make a hard effort to construct the database, and we make some works to define an architecture that are the best possible to mimic exactly the denoising capability of this method, and that's we call it. It's why we call it virtual PDHM, and it provides some very interesting results. It's some things we are present not in detail in this symposium, and we are submitted some paper about these new techniques. So what is important here is to understand what is makes the job great. It's not the architecture or something like that. It's the database, okay? Or what is the more important in this kind of techniques is the construction of your database. Another illustration, same field, same architectures, same procedure. We can use CNN to make noise reduction in the field of electron microscopy. For instance, here in transmission electron microscopy, we have some also example in IFPN for secondary electron microscopy or scanned electron microscopy also. The idea is the same. Take time to construct a database where you have a standard image and denoised image with experimental technique, and you use it to train a network to mimic the job. Here it's a work done with IPCMS with Saoudia Traoré, where he was in postdoc in Strasbourg. IPCM is a laboratory from Strasbourg. Okay, and I think it's the last example. We can use also CNN, same architectures, okay, with as UNet, to estimate deformation map or displacement field of some object. The idea is to provide at input two images, almost two images, okay? For instance, an image and deformation of an image, or if it's a video, you use an image at time t and you use the second image at time t+1, okay? You use a CNN and you train the CNN to estimate a displacement field. So here I just show one image, but it's also two images. You have the component in X and Y of your displacement, okay? So here you have a video, so you can see exactly what is done. So you have some microfluidic experimental microstructures where you have microglotlets that travel inside this microstructure. The idea is to estimate the speed and the displacement field of this kind of object. It's a work from Elliot Spears, PhD student, former PhD student, and a colleague from ERP, Marie-Caroline Julien. Sorry. So you provide two images of your video, and the CNN provide you the displacement field of the two between the two images. It can be used also to compute some deformation into materials and something like that. Okay, so I provide a lot of examples that are available in the software that is called Plugim. It's a free software. It's developed by EFPAN. It provides a lot of tools to make signal processing, image processing, but also virtual material design. So with Plugim, you can simulate some 3D microstructure of material and compute some textural property in 3D or elastic property or something like that. It's completely free, so don't hesitate to visit the website. And what it's important, and it's in correlation with the lectures, you can find in the website two tutorials. One tutorial concerning semantic segmentation, okay, and one other that is quite similar for the noise reduction. So it provides you some way to install Python environment. It gives you some Jupyter notebook and Python script to make the training yourself. So you are able with this tutorial to train yourself networks. And then you have your network train. You can use it with Plugim, with a standard plugin. Okay. So don't hesitate to take a look to these two tutorials. Okay. So I go to the conclusion. So I hope I present you some things and I convince you that deep learning, especially what we call here, it's deep learning in a principle fact, it's a new standard tools, especially in image and signal processing. And now you know it with ChatGPT and so on, also in text processing and generative process of processing text or images. It's a very good classification method, and a lot of problems can be formulated as classification problems. Okay, it's a way of see those things. You can see those things in other way also, but it can see with as a classification method, as I explained it before, and you can understand a lot of problems like this. So in the field of image and signal processing, you will see a lot of convolutional neural network. And it's because, as I explained before, it's a way to correctly consider image-like data structures, where the spatial arrangement of the data is of primary importance. That's why convolutional networks is very useful. For the text, you see in a large language model, for instance, in ChatGPT or so on, and all of this kind of LLM, you don't see convolutional neural network, you see transformers, because transformers is a very good operator to make some correlation with high detail where you are very close, but also if you are very far. And it's the case in the text. You want to make some similarity between the words that just neighbor of the two consecutive words, but in some case, you need to make some similarity with the word that in the previous sentence or in the next sentence to keep some sense of your text. So that's why it's not convolutional neural network are not used for text processing because it's not well adapted, but we use transformer. You can see some transformer also for the image processing, but for me, it's not a very good operator. CNN, it's better to do like the same things. Something is important, considering the theory and mathematical point of view. There is still a lot of questions about the ability to generate a learning. So we see that it works, but it's not so easy to make some proof or to explain it in detail what it generates so good and why the learning procedure is so efficient. So there is a lot of questions, and I think it will be interesting to go in detail into this question in the next years. And important things, very important things, is the creation of database. These methods are completely linked into the quality of your database. Okay, it's not the architecture. The primary order importance is the database. So your database to solve your problem need to be representative and unambiguous. So it's some things you need to take with you at home. It's this information for deep learning. What is very important is the database. First things. Okay, and I will stop here. Thank you for your attention, and I'm open for another question if you have. Thank you.
Thank you for the presentation. For the semantic segmentation for the electron tomography.
Yes.
I had a question about the size of the data that you guys worked with. Do you have any information about the size of the data? How long did it take to actually do the segmentation? Because I'm working on a similar project.
So if I go back to the, I think you speak about this application?
Yes.
Okay. So in this application, we deal with, to be very practical, the size of the volume in electron tomography is about classically 1,000 by 1,000 by 1,000 pixels. Usually we only work with a crop of this volume. It's 500 by 500 by 500, okay? To make the training procedure with this kind of technique with contrastive loss, or it can be also with UNet standard method. It's more efficient with contrastive loss, but it works also with standard method, supervised method. It can be done only with the annotation, for instance, five slices of your volume to be able to segment it correctly. You need to take it carefully to select carefully your slice. So as I mentioned at the conclusion, it needs to be representative. So you need to take some slice where you have all the contrast or a lot of contrast that are representative to your object. You need to take some slice where you have some characteristic noise or artifact reconstruction noise present in the slice to be able for the CNN to understand what is the information and need to be kept and what is the noise, okay? But in this kind of problem, yes, you can make quite good segmentation using only 5 slices. With the work with Cyril, we try to do the same result with less than 1 slice. It's some things where you want to go very fast and take very small time to make the annotation. But in classical, in practical way, it's not so big deal to take time to annotate 5 slices and obtain something very interesting to obtain your data extracted.
Okay, and do you have an idea about the time it took to actually train and annotate, and what, like, how much data did you annotate?
Okay, so if you take, for instance, as I mentioned, 5 slices to annotate, you will use a procedure to increase the size of your data. So you will, for instance, use patch procedure. Okay, you will that I don't explain it in my lecture, but you can use also data augmentation, standard data augmentation. So the idea is to use tricks to increase the number of patch using some rotation of your patch or some degradation where you use some noise in your patch. In this kind of, electron tomography, it's not a good idea to use to add noise, but it's a good idea sometimes to make some slight deformation of your object. Not too much because artifacts are oriented. So if you make some too much orientation, it's not correspond of the problem you want to solve. So it's not relevant for the training. Training is always related to your problem you want to solve. So you need to think about what the data I need to select to solve my problem to be able to understand it very well. So to be more specific, the training is not very long. It can be in the order of 1 hour or 2 hours maybe. And the segmentation can be done also. Can be fast. If you want to done it very fast, you can do it. If you, for instance, you can have the segmentation unit with less than 1 second, okay? And you have 500 slices, so maybe it's several minutes to make the segmentation. But if you want, you can make efforts to make the implementation more efficient, and you can be able to segment a volume with less than 5 seconds if you want, or maybe 10 seconds.
And my last question, you're treating the problem as 2D slices instead of actually, okay. Thank you.
Exactly. It can be better if you want. You obtain quite good result only with slice, but if you want more accurate results, you can take into account the next and the previous slice. It gives you a lot of information concerning the 3D arrangement of your voxel, and generally it's sufficient to increase the quality, the accuracy of your results. You don't take the next and the previous slide. For the segmentation procedure, I speak. It increases the accuracy of your result. Yes. Thank you for the question.